Hello, and welcome to today's lesson on logical reasoning. This is going to cover topics in the standard 1.1 in geometry and in the study island lesson, logical reasoning. So if you're working in either of those two places, this is where you want to be. And this is going to be one of two parts over the lesson of logical reasoning. There's a lot of information in that little study island lesson, so I needed to break it up. In this part, we're going to be covering the questions that deal with always, sometimes, or never, law of syllogism, and counter examples. So if you're stuck on any of those types of problems, that's what we're going to be doing today. Just remember that geometry is very vocabulary rich, and so you're going to have to study those vocabulary words and the rules and the theorems and just get them in your head so that you can pull from them. Because once you have them in your head, these problems should go fairly easy for you. So you should be taking a little bit of time every day to study your notes and your vocabulary. So that can help you to be more successful. And these questions in logical reasoning, they also pull from all of your geometry knowledge from all year long. So if you're struggling with something, it might be because maybe you haven't got that far in your geometry class yet. So go ahead and look up the words that you don't know to see how you can do. And then that also helps you to know, oh, these are the definitions I need to study more. So I am so glad that you are here. And let's go ahead and look at some examples.
First, we're going to look at the problems that ask you to state whether this always, sometimes, or can never happen. So to look at these, they're going to give you an inequality or an equation, and you're going to want to solve that first. And if you solve all the way through and your variables disappear, and you're left with just a number equal to a number, such as 5 equals 5 or negative 2 equals negative 2. If it's the same number, so it's something that makes sense, like 5 equals 5, that makes sense, then that problem is always true, aka that variable in the original inequality or equation can be any number. So because it can be any number, it will always be true, because you can pick any number and it'll become true. Now, if you do that and all the variables disappear again and you're left with a number equals a number again, but those numbers are different, such as 5 equals negative 3 or 2 equals 1, negative a half equals 52, okay, that's never going to be true. There's no number out there that can be substituted in for that variable to make that equation or inequality true. Now, if you work it out and it comes out to be something that you're used to seeing, such as x equals a number, or x is less than a number, or any inequality there, less than, greater than equal to, less than or equal to, then that problem is sometimes true. So that means the variable can be one or some number. So if it's an equal sign, it can be that one number, or if it's an inequality, it can be any number that makes that true. Okay, so let's look at some problems. Okay, so state whether the following is true sometimes, always, or never. So I'm going to go ahead and work out this problem, and I'm going to combine like terms first. And so I'm going to move these x's. They are like terms. Now they're on opposite sides of this equal sign, so that means I'm going to have to change the sign. Different signs, different side, different signs. So to keep this equation balanced, I subtract 30x from both sides. 30x minus 30x is 0. And then once again, 30x minus 30x is 0. So that means I'm left with 216 equals 6. This is what I mean when your variables disappear. They just all cancel it out when I try to combine like terms. And I'm left with a statement that doesn't make sense. 216 does not equal 6. So this is going to be never true. Okay, this is the same type of problem. This time I have an inequality instead of an equation, which is fine. I'm going to go ahead and combine like terms again. I have x's on opposite sides, so that means when I combine those like terms, I'm going to have to use opposite signs. So I'm going to subtract 3x from both sides. 4x minus 3x, I'm left with a single x. and then I still have my minus 8 less than or equal to, and then I still have that minus 7 or negative 7. Okay, so now I'm going to go ahead and add 8 to both sides so I can continue to get x by itself. These 8's cancel, and I'm left with x is less than or equal to negative 7 plus 8 is positive 1. Well, this is saying that I can use any number less than or equal to 1 to make this equation true. So that means that it's sometimes going to be true. For the numbers that are greater than 1, it's not going to work out. But any numbers less than or equal to 1, 0, negative 1, negative 2.5, they're going to make it true. So that means it's sometimes. Okay, this one is same type of problem. I have to solve my equation first. I have parentheses. So I'm going to distribute the negative 11 out front, which means I take negative 11 times x, which is negative 11x. And then negative 11 times that minus 5 is a positive 55. So I write plus 55. And then my second side stays the same. So I have 55 minus 11x. I have x's on either side here. So I'm going to go ahead and combine those like terms. But when I bring this 11x over here, it's a minus 11x. So when it changes sides, I have to switch signs. So I'm going to add 11x to both sides. Okay, those are going to cancel out, but negative 11 plus 11x on this side also cancels out. And I'm just left with 55 equals 55. Well, that makes sense because 55 is the same as 55. So that's always going to be true because my variables all disappeared and I'm left with a number equal to that same number. The second type of questions we're going to look at today are ones that use the law of syllogism. And the definition of the law of syllogism is that if you have statements that we're going to call P, Q, and R, but those just represent some statement. So triangles have 3 sides. Triangles add to 180 degrees, like some statement like that. So if you have a statement that says, if you know this, then this will occur, but then you know that second part, and then this also occurs. Then it just says that you can eliminate this middle part. You can go straight from the beginning to the end without having to say that middle part. So this is how the definition is written. Let's go ahead and look at some examples so that you can see it that way also. Okay, this problem says, use the law of syllogism to draw a conclusion if possible. So we have these statements, if a number ends in 0, then it is divisible by 10. If a number is divisible by 10, then it is divisible by 2. Do you see how this one ended and this one began with the same statement? If you have that repetition from the end to the beginning, that means you can go ahead and just eliminate that part and say, if a number ends in 0, then it is divisible by 2. That's what the law of syllogism says. So here, the answer that says that is letter A. So that's going to be your answer. Here's another example that asks us to use the law of syllogism to draw a conclusion if possible. And I have these 2 statements. If a shape is a square, then the diagonals are perpendicular. If the diagonals are congruent, then the shape is rectangular. Now, when I look at the ending of my first statement and the beginning of my second statement, they're different. So I can't use the law of syllogism. So this one's letter A. It is not possible to draw a conclusion because these aren't the same statement. Okay, there's another example. We're using the law of syllogism to draw a conclusion if possible. The statements we're given is if the diameter of a circle is 20 centimeters, then its radius is 10 centimeters. If the radius of a circle is 10 centimeters, then the area is 100 pi centimeters squared. So when I'm looking at the end of my first statement and the beginning of my second statement, they have it's the same statement. So I can go ahead and eliminate that middle part and just look for the answer that gives me if the diameter of a circle is 20 centimeters, then the area is 100 centimeters squared. And the answer that gives me that is D, so D is my answer. The last type of question we're going to look at in this part is ones that ask you to give a counterexample. So the definition of a counterexample is it refutes or disproves an assertion. Counterexamples are often used in math, logic, and philosophy. It only takes one counterexample to refute or disprove an assertion. So when you're asked to give a counterexample, this is very helpful because you only need one. It's a lot easier to prove something is wrong than it is to prove something is right. So let's look at an example to help you understand the definition. It says a square and a rhombus are the only quadrilaterals that have two pairs of congruent adjacent sides. Which of the following is a counterexample of this assertion? Now, there might be a bunch of words in this problem that you're not real sure what they mean. So you can go to this website I have pulled up here, mathwords.com/index_geometry.html, and it lists the definitions of every possible geometry word you might see. So here, let's say you're not sure what rhombus means. So we're going to go down to the R's and look for rhombus. Right here. So I'm going to click on it, and it tells me all about the rhombus. It gives me a picture, area, formulas, and all that. So a rhombus is a parallelogram. It has four congruent sides, and note that the diagonals of a rhombus are perpendicular, and a square is a special kind of rhombus. So that means a square is an example of a rhombus. So here it wants to know, okay, are a square and a rhombus the only two pairs of that have congruent adjacent sides? So a rectangle, adjacent means they touch. So a rectangle, the sides that are the same, that are congruent, don't touch. So I know it's not a rectangle, but I'm not sure what a kite is. So I'm going to go over here and click on kites. And the definition here says a quadrilateral with two pairs of adjacent sides that are congruent. So this one is something that has congruent adjacent sides. So that's going to be my counterexample because it proves that there is another shape. So my answer here is A. And that also tells me, okay, I need to copy this definition down for kite and memorize it because it's something I don't know. But that way you can still work through the problem and get the right answer. This next example says, given a triangle with sides 4, 8, and x, so some number we don't know, the perimeter can be between 15 centimeters and 23 centimeters. So which of the following is a counterexample to this assertion? Well, to do this, I have to remember that there is a triangle inequality theorem that says the sum of the lengths of any two sides of a triangle is greater than the length of the third side. So that means that if I add any two sides, that sum has to be bigger than the remaining side. So if I look at letter A, if I have a perimeter of 17, and I know that 4 and 8 is 12, that means my fifth side is going to be 5 centimeters. Because that's what if you add 4 plus 5 plus 8, that gives me the 17. So if I add 4 plus 5, that's 9. That's going to be greater than 8. So that one does exist. Okay, so if I look at that triangle does exist. So if I look at my next perimeter, it's 16.5. That means my third side has to be 4.5 centimeters. Because when I add 4 plus 8 plus 4.5, that gives me the perimeter of 16.5. Well, if I take the two smaller ones, 4 plus 4.5, that's 9.5. 9.5, that sum is bigger than 8, so that triangle does exist. So if I look at the perimeter 15.5, that means my third side has to be 3.5 in order to add all three sides and get a perimeter of 15.5. And if I take my two smaller ones, 4 plus 3.5, that gives me 7.5. 7.5, that sum isn't bigger than 8. So that means I can't have a perimeter of 15.5. So C is going to be my counter example. Thanks for joining us today, and I hope you learned something new.